take the lines away, the most interesting star, I think, the star that could be shocking in our sky is this one, Betelgeuse or Betelgeuse. It's a red giant star. If you put it where the sun is, it would extend out to the orbit of Jupiter. It's enormous. It's very unstable. It's about to explode.
In recent weeks, the James Webb Space Telescope has made astounding discoveries, but one recent discovery stands out as this revelation has sent shockwaves throughout the scientific community. Astronomers recently directed the James Webb Telescope to Betelgeuse, which is a prominent star in the night sky. The telescope detected an unusual sign, which was immediately interpreted and analyzed by the scientists. What they found caused huge concerns, as it suggested the potential for a massive supernova explosion. Particularly, Brian Cox, a renowned British physicist, believes that the Betelgeuse supernova is imminent and could occur at any moment. This development has raised many questions about the implications for Earth and the severity of the effects resulting from the unprecedented supernova event. Join us today in this exploration as we delve into the James Webb Telescope's unsettling announcement regarding the Betelgeuse's impending explosion and what Brian Cox has to say about it. Betelgeuse is classified as a supernova due to its extraordinary size and power, presenting a celestial marvel that baffles scientists with its irregular pulsations and high unpredictability. A star is required to be at least 8 times more massive than our Sun to be considered a regular supernova. The sheer enormity of Betelgeuse sets it apart, as it is 700 times the size of the Sun and 15 times more massive. The Betelgeuse supernova continues to awe researchers with its inexplicable extremes. In a recent research study, scientists used the James Webb Space Telescope as well as the Laser Interferometer Gravitational Wave Observatory, ain't that a mouthful, to capture celestial phenomena in space. Scientists were immediately taken aback after reviewing the data, as it revealed a light wave emanating from the Orion constellation. Positioned at the left shoulder of Orion, Betelgeuse falls into the category of semi-regular variable star, meaning it dims irregularly. This irregularity allows us to gauge its distance from Earth, approximately 475 to 642 light years away. The Betelgeuse supernova experiences dimming roughly every 430 days. And during each 6-year cycle, the dark spots emerge on its surface. Analogous to dark spots on our Sun, albeit on a grander scale. In February of 2021, the supergiant underwent a particularly dim cycle, registering a V-band magnitude of plus 1.614. Still relatively bright, but dimmer than its average luminosity. Betelgeuse's brilliance isn't the only distinction of this supergiant, though. Its iconic reddish tint stems from a surface temperature of around 3500 Kelvin, which is notably cooler than our Sun, sitting at approximately 5500 Kelvin. Due to this lower temperature, Betelgeuse emits less energy per unit of surface area compared to our Sun. Despite being among the largest stars known to us, its diminished energy output makes it appear dimmer than expected. Perhaps just content to let the other stars take the spotlight, Betelgeuse has long graced our night skies as one of the most prominent celestial bodies. Its recognition dates back to the Greek astronomer Ptolemy, who described its color as more of an orange tawny, a time when star attributes were limited to things like color and position in the night sky. Modern astronomy, empowered by advanced instruments and technology, meticulously measures the intricacies of celestial bodies. Analyzing Betelgeuse's emitted light has unveiled details such as its size, temperature range, and chemical composition. The Hubble Space Telescope, with its detailed images, has exposed the red supergiant's surface, unveiling distinctive patterns of gases as well as dust clouds. These observations enable scientists to construct accurate models of the star's behavior, providing insights into its future evolution. ALMA, an advanced observatory in Chile, delivered ultra-high resolution images of Betelgeuse's surface, unveiling significant insights into the structure and behavioral patterns of this red supergiant. Among the remarkable discoveries facilitated by ALMA's technology is the identification of an expansive gas plume extending from the star's surface. This plume, believed to be induced by Betelgeuse's pulsations, offers a potential explanation for the star's distinctive behavior and ongoing transformations. The pulsations, triggered by convection, involve the upward movement of hot gases and the downward movement of cooler gases. This cyclical motion generates waves that traverse Betelgeuse's atmosphere, causing it to expand and contract. Betelgeuse's surface features dark spots, known as star spots or magnetic spots. These spots correspond to regions where the star's magnetic field is most potent. The magnetic fields create cooler areas compared to the surrounding gas, inhibiting the flow of hot gas from the star's interior to its surface. Believed to be several thousand times stronger than the sun's magnetic field, Betelgeuse's magnetic field traps gases in loops, resulting in zones of intense magnetic activities visible as dark spots in the images. Star spots, a common occurrence, are not exclusive to Betelgeuse. Many stars, including our own sun, exhibit these features. The dark spots on Betelgeuse's surface are believed to be significantly larger than Earth, covering up to 20% of the star's surface. These star spots directly impact a star's brightness, causing fluctuations over time. The more star spots present, the dimmer the star becomes. This occurs because the areas covered by the dark spots are cooler, emitting less light compared to the regions with weaker magnetic fields. Now, the recent gravitational wave readings from Betelgeuse have stirred concern among astronomers. The discussed dimming is a common behavior in stars approaching the end of their lifespan. The challenge lies in the fact that stars of Betelgeuse's magnitude don't fade away quietly. In other words, they don't go out without a bang. Supergiants exit dramatically with a supernova explosion, befitting their size, brilliance, and magnificence. Scientists are now contemplating the likelihood of Betelgeuse undergoing such a supernova explosion. If it does, researchers hope that it happens soon, as such an event would offer invaluable insights into the cosmos. If Betelgeuse were to end in a spectacular ball of flaming gases, the effects of the supernova would be observable from Earth, even in the brightness of day. The signs and data emanating from Betelgeuse affirm that it's only a matter of time before this red supergiant bids farewell to the cosmos. However, pinpointing the exact time frame for this cosmic exit remains undetermined. Recent data gathered by the James Webb Space Telescope and the Hubble Space Telescope indicates that just a few years ago, the red semi-regular variable star underwent a significant eruption, losing a substantial portion of its visible surface. This explosion has triggered a considerable surface mass ejection from Betelgeuse, raising questions about whether it is on the brink of a complete explosion. The magnitude of this massive ejection, with substantial dust clouds, is an unprecedented occurrence for scientists. It deviates from the typical behavior of both young and dying stars. While our sun experiences minor outer atmosphere losses in coronal mass ejections, they pale in comparison to the intensity of Betelgeuse's ejection. Observations from the James Webb Space Telescope reveal that the red giant is gradually recovering from the substantial ejection. Despite ongoing scrutiny from scientists, the recent phenomena surrounding Betelgeuse remain a source of puzzlement. The star's recent activities provide an invaluable learning curve for scientists as they strive to unravel the complexities and mysteries of this celestial giant. Observations from the James Webb Space Telescope shed light on the process of how red stars shed mass as they approach the end of their life cycle. Scientists have uncovered that these stars lose mass as their nuclear fusion furnaces begin to extinguish before culminating in multiple supernovas, or supernovae, if you will. The extent of mass loss significantly influences their fate. The recent substantial loss of mass by Betelgeuse indicates a likely prelude to the demise of this colossal red star. This development has stirred heightened concern among scientists and astronomers alike who are diligently working to obtain more definitive understanding of these occurrences. The huge ejection of mass by Betelgeuse is believed to have originated from the convective plume that spans over 1 million miles across its surface area, emerging from the star's depths. This plume generated powerful pulses and shocks, leading to the expulsion of a portion of the star's photosphere, creating an expansive cool surface area. Beneath the dust raised by this mass ejection, Betelgeuse grapples with recovery from this significant upheaval. The lost mass, weighing several times more than our moon, dispersed into space, cooling and forming a dust cloud that obstructed the star's light from reaching Earth. This obstruction resulted in a conspicuous dimming of Betelgeuse in 2019, lasting for several months. The dimming was so pronounced that even amateur astronomers, lacking sophisticated instruments, observed the marked reduction in the star's brilliance. For over 2 centuries, scientists and astronomers alike have meticulously observed Betelgeuse's rhythms and movements, documenting the noticeable disruptions that underscore the profound impact of this blowout of the star's photosphere. Analyses from the TRES and Hubble spectra suggest that while the outer layer may return to normal soon, the star's surface remains in a precarious state, awaiting the completion of the photosphere's rebuilding process. While our sun has experienced coronal mass ejections, the stark difference in magnitude between the sun's ejections and the recent surface mass ejections from Betelgeuse emphasizes that these events cannot be equated. Betelgeuse's expansive growth over millennia is evident, and if it is occupied by the sun's current position in the cosmos, its outer orbit would extend beyond Jupiter's orbit. The red hue of Betelgeuse indicates that the star has reached the stage where stellar bodies deplete their hydrogen reserves, leading to the collapse of the core and the puffing out of the outer layers. In contrast, our sun is still relatively young and has a long journey ahead before reaching this mature stage. Scientists estimate that it will take another 5 billion years for the sun to reach such maturity. When it does, projections suggest that its radius will expand to proportions reaching Mars's orbit. Following the significant dimming of Betelgeuse in late 2019, scientists closely scrutinized the star's altered behavioral pattern. Although the supergiant star regained its brilliance within months, scientists were intrigued by the initial cause of the dimming. Various hypotheses were proposed, including the idea that it resulted from a star contracting before an impending explosion, signifying the red giant's demise. However, data from NASA's James Webb Telescope dispelled this theory, revealing that the apparent dimming was solely due to the dust clouds raised from the ejection. With this puzzle resolved, scientists now believe that the supernova event is not expected for another 1.5 million years. It has been confirmed that Betelgeuse's color transformed from a yellowish orange to red over the last 2 millennia. Combining this information with theoretical calculations, indicating the star is 14 times larger than our Sun, allows the deduction that Betelgeuse is approximately 14 million years old. This deduction positions the red supergiant in its late evolutionary stage, with expectations that it will explode and cease to exist in the next 1.5 million years. Some scientists argue that merely detecting gravitational waves from the aging red star is insufficient to predict its impending demise. According to Salvatore Vitali, a physics professor at the Massachusetts Institute of Technology, the detected wave coming from the direction of Betelgeuse may not necessarily originate from Betelgeuse itself. Vitali emphasizes that just before a supernova occurs, neutrinos are typically released, which has not yet occurred in the case of Betelgeuse. Additionally, the fact that Betelgeuse still illuminates in the night sky, albeit dimmer than usual, makes it an unlikely source for gravitational wave emission. There's even uncertainty as to if the intercepted wave is indeed a gravitational wave, as it lacks the characteristics of known mergers, leaving the cause of the detected wave shrouded in mystery. While the possibility of earthly disturbances causing noise in the detection has been ruled out, the exact nature of the wave remains elusive. Supernovas, despite their visual allure, pose significant dangers, releasing high-energy radiation upon explosion. The gamma rays emitted can be thousands of times more potent than the energy from our Sun, and if directed towards Earth, could potentially harm terrestrial life by damaging DNA. The debate among researchers about Betelgeuse's potential supernova is ongoing. Some speculate that its time is nearing its end, while others argue that the red giant may have tens of thousands of years left. The most recent supernova observed in our Milky Way galaxy was in 1604, although there could have been subsequent nearby supernovas hidden by atmospheric gas and dust. Instances like the Crab Nebula, originating from a supernova in 1054, serve as remnants of past explosive events. The 1987 supernova in the Large Magellanic Cloud and the Kepler supernova are among the more recent observable occurrences in galaxies beyond our Milky Way, highlighting the dynamic nature of the universe. In simpler terms, witnessing a star explosion in our galaxy is a rare occurrence. Astronomers estimate that our galaxy experiences an average of 1 to 3 supernovae every century. Today's astronomers are better equipped for such events compared to astronomers of Kepler's time. Modern telescopes can capture visible light, providing insights into how supernova would appear if observed nearby. Also, infrared telescopes like the James Webb Space Telescope extend beyond visible light, penetrating gas and dust to reveal celestial objects not visible with conventional telescopes. Apart from light observation, scientists can also detect neutrinos and subatomic particles emitted by supernovae, using specialized detectors. Moreover, detectors for gravitational waves, minor vibrations in space and time, offer another dimension to supernova study. Supernovae came into 2 main types. Type 1 involves the white dwarf star undergoing a runaway nuclear reaction, while Type 2, or core collapse supernova, results from a star collapsing under gravity after running out of nuclear fuel. Type 2 supernovae are particularly intriguing as they emit not only light but also a significant amount of neutrinos. Neutrino emission may precede the explosion, allowing detectors to pick up signals hours or even days before the visible explosion occurs. Betelgeuse has experienced recent brightness fluctuations, leading to the speculation about a potential supernova explosion. However, recent research suggests that the dimming may be attributed to dust clouds or sunspot activity on the star's surface. Despite this, anticipation remains for the eventual explosion of this massive star. Astronomers have established the supernova early warning system, also called SNEWS, a network of neutrino detectors across various countries, including Antarctica. SNEWS will automatically alert astronomers if galactic supernova neutrinos reach Earth, providing valuable data for studying the event. The upcoming SNEWS 2.0 aims to enhance triangulation capabilities. Neutrino science has evolved since the 1987 A supernova, with the potential for thousands or even hundreds of thousands of neutrinos to be captured by the global detector network during a galactic supernova. In the event of a collapsing star forming a black hole, the abrupt cessation of the neutrino stream could signal this phenomenon. Astronomers, in their search for missing stars, may identify potential black hole locations by observing blank spaces in lists of known stars. Massive stars, though celestial celebrities, undergo destructive supernova explosions. Despite their captivating nature, proximity to Earth raises safety concerns due to the potential dangers of an explosion within a specific minimum safe distance. Evidence of a starburst near Earth around 3 million years ago has been found through the presence of radioactive iron atoms, iron 60 or 60 Fe, in lunar cores and deep ocean samples. These unique atoms serve as traces of supernova explosion remnants, allowing scientists to study the nuclear processes driving exploding stars and uncover events predating recorded human history. Furthermore, a nearby supernova, such as the one that occurred in close proximity to Earth, likely released significant radiation, posing potential hazards. Throughout Earth's 4.5 billion year history, the planet has encountered various challenges, including enormous impacts, volcanic eruptions, and episodes of snowball Earth. Despite these challenges, life persists. Analogous to fireworks on Earth, supernova explosions offer a spectacular view from a distance, but can be perilous for onlookers in close proximity. Neighboring supernovae can impact biospheres on Earth-like planets through two mechanisms. Initially, high-energy gamma rays are emitted in the first few weeks and months, which, although blocked by Earth's atmosphere, cause severe damage to the ozone layer. Subsequently, high-energy cosmic rays arrive with an explosive blast wave thousands of years later, harming the ozone layer and directly irradiating terrestrial and marine life with penetrating muon particles. Certain supernovae release prolonged and intense X-ray radiation for up to a decade following the explosion, posing a serious threat to the ozone layer. The danger radius for these X-ray bright supernovae is extensive due to their potent X-ray emission. Consequently, these relatively infrequent events pose a threat comparable to more common explosions. In essence, the galaxy's danger levels has heightened. Supernovae, with their destructive potential, can annihilate biospheres and expose worlds to lethal radiation. Recent research indicates that a specific type of supernova can destroy a planet's ozone layer years after the explosion, introducing a new potential hazard. Despite the combined brightness of hundreds of billions of stars, a single supernova has the capacity to eclipse its luminosity. Putting things into perspective, imagine Betelgeuse on the verge of exploding. Despite being over 600 light-years away, when it goes supernova, it will become the second brightest object in our sky, outshining even a full moon, and visible during the day. The dazzling display will cast shadows in the darkest hours. While a supernova's visible light emission is only the fraction of its total energy production, the high energy radius it emits, primarily in the form of X-rays and gamma rays, raises concerns. Although exposure to intense visible light may cause blindness, its detrimental impacts are generally limited. The real threat lies in high-energy radiation, capable of catalyzing oxygen and depleting the ozone layer. exposing life on Earth's surface to the full force of the sun's UV radiation, potentially leading to an extinction event. The initial seconds of a supernova unleash a radiation blast, but the greater danger emerges hundreds or millions of years later when cosmic rays, accelerated subatomic particles, erupt from the aftermath. These cosmic rays can shred ozone layers and inundate planetary surfaces with lethal radiation. Evidence of significant levels of iron-60, a radioactive isotope produced solely in supernovas, found in deep-sea cores and lunar regolith, suggests Earth might have been struck by a supernova ejecta in the last few million years. While astronomers have reassured us about the absence of imminent supernova candidates threatening life here on Earth with gamma rays and cosmic rays, a new potential threat has emerged. A specific type of supernova, occurring when a dying star is surrounded by a substantial disk of material, has the capacity to emit long-range and hazardous radiation, posing a danger to Earth-like worlds. This scenario arises when a shockwave generated by the supernova explosion strikes the surrounding disk, causing it to become extremely hot and emit significant X-ray radiation. This radiation possesses high energy density and an extensive range of travel. Recent astronomical studies suggest that the brightest X-ray supernovas could deplete a planet's ozone layer by up to 50%, leading to a potential extinction event with a remarkable distance of 150 light-years. Such supernovas would deliver a lethal combination, bombarding a fragile planet with X-rays months or even years after the initial burst, followed by cosmic rays arriving hundreds or thousands of years later, completing the devastation before the biosphere could recover and regenerate its protective covering. Theoretically, life on Earth could be endangered by a close supernova, but that explosion would need to be in close proximity. Fortunately, no imminent supernova candidates pose a threat. While a close supernova's radiation blast could be disastrous, releasing gamma, X, and UV radiation over a few weeks, the impact would depend on the proximity of the explosion. Past geological records hint at a potential link between a global extinction event at the end of the Denovian period around 360 million years ago and a supernova, evidenced by sunburned plant spores found in rocks from that time.